Time feels constant until it doesn't. Every second of your life feels the same. One tick, one moment, one steady flow forward. It feels universal, reliable, unchanging. But what if that feeling is wrong? What if time does not move at the same speed for everyone, everywhere, all the time? Here is a fact that sounds impossible, yet has been proven again and again. If you move faster, time slows down. Not in your mind, not as an illusion, in reality. This isn't philosophy, it's not science fiction, it's physics. Astronauts age more slowly than people on Earth. Satellites experience time differently than your phone. Even airplanes change the flow of time, slightly, just by flying. Time is not fixed. It bends, it stretches, it responds to motion. And the faster you move, the more dramatic that effect becomes. Tonight, we're not asking how time feels. We're asking how time actually works, why motion changes it, why we don't notice it, and how the universe forces time to slow down, to obey one unbreakable rule. To understand why time slows down in motion, we have to start with something deceptively simple. We have to start with why time feels constant to us in the first place.
Why time feels constant, and why that's an illusion. From the moment you are born, time appears perfectly steady. Seconds feel equal, minutes feel predictable, days follow nights without variation. This consistency is so convincing that we rarely question it. Time feels like a background feature of reality, like space, like air, always there, always the same. But this feeling is not evidence, it's a limitation. The human scale problem. Humans experience the universe at extremely low speeds. Even a fast car moves at about 30 meters per second. A jet aircraft moves at around 250 meters per second. These speeds feel impressive to us, but compared to the universe, they are almost zero. Light travels at 300 million meters per second. That difference matters, because time only begins to behave strangely when motion approaches that scale. Why everyday life hides relativity. At human speeds, the slowing of time is real, but incredibly small. So small that your brain cannot detect it, so small that your body cannot feel it, so small that clocks barely register it. That creates a powerful illusion, the illusion that time is absolute. The assumption of a universal clock. For most of history, people believed time worked like this. There is one universal clock. It ticks the same everywhere. Everyone shares the same now. This idea makes intuitive sense. If you and I look at a clock, we expect it to agree. But intuition is not a law of nature. The first cracks in the old idea. In the late 1800s, scientists ran into a serious problem. They discovered something unsettling. No matter how fast you move, the speed of light never changes. Not for observers standing still, not for observers moving fast, not even for observers chasing the light itself. Light always moves at the same speed. This single fact shattered everything scientists thought they knew about time and space, because something had to give. Why constant light speed breaks time. Imagine you're riding a train. You turn on a flashlight and point it forward. Common sense says someone standing on the ground should measure that light is moving faster than someone sitting on the train. But experiments showed that doesn't happen. Both observers measure the same speed of light. So how is that possible? The answer is disturbing. If speed cannot change, then time must. Time adjusts to protect light. To keep light speed constant, the universe makes a trade. Distances change, durations change,
Clocks tick at different rates depending on how fast they move. This isn't optional, it's required. If time did not slow down in motion, the laws of physics would contradict themselves. Motion forces time to bend. At low speeds, the effect is tiny. At high speeds, the effect becomes dramatic. Two observers moving relative to each other will disagree about how long events take, when events happen, whether events happen at the same time. This means something radical. There is no universal now. Why you never notice this? You and everything around you are moving together. Your house, the earth, the atmosphere, all share nearly the same motion. Because of that, your clocks agree, your body agrees, your experience feels consistent. But consistency does not equal absoluteness. It only means you are not fast enough to expose the difference. Earth is already slowing time. Even standing still, you are moving. Earth rotates, Earth orbits the sun orbits the galaxy. You are traveling through space at hundreds of kilometers per second, and because of that, time for you is already slightly slowed compared to a hypothetical observer at rest. The effect is small, but it is real. Time is not a river. We often describe time as a river flowing past us. That metaphor is wrong. Time is more like a fabric. It stretches, it compresses, it responds to motion, and motion is the key. In the next part, we'll see exactly how motion slows time, not conceptually, not metaphorically, with real experiments, real clocks, and real proof that time does not tick the same for everyone.
Einstein's discovery: why time must slow down. At the start of the 20th century, physics was in trouble. Not because scientists lacked equations, but because the universe refused to behave the way common sense expected. The problem no one could ignore. By the late 1800s, experiments had proven something shocking. The speed of light is constant. No matter how fast you move, no matter which direction you go, no matter how you try to measure it, light always travels at exactly the same speed. This result made no sense because according to everyday logic, speeds should add together. The intuition that failed. Imagine standing still while a car drives past you. If the car moves at 60 miles per hour and throws a ball forward at 20 miles per hour, you measure the ball moving at 80 miles per hour. That's how motion works. Except, light refused to follow this rule. Even if you chase a beam of light, you never measure it as moving slower. You still measure the same speed. This wasn't theory, it was experiment, and it broke physics. Enter Albert Einstein. In 1905, a young patent clerk named Albert Einstein made a radical decision. Instead of questioning the experiments, he questioned time itself. Einstein proposed something revolutionary. The speed of light is constant for all observers, and the laws of physics are the same everywhere. If both statements are true, then time cannot be absolute. Why time has to change. Here's the key idea. If two people are moving at different speeds and both measure light moving at the same speed, then something else must adjust. Distance can't change arbitrarily, so time must. This is not philosophy, it's mathematical necessity. The light clock thought experiment. Einstein explained this with a simple idea. Imagine a clock made of light. A beam of light bounces between two mirrors. Each bounce is one tick. Now imagine two versions of this clock. One is standing still, the other is moving very fast. To an observer watching the moving clock, the light beam travels a longer diagonal path, but the speed of light cannot change.
So if the path is longer and speed is constant, the time between ticks must increase. The moving clock ticks more slowly. This isn't an illusion. Nothing is wrong with the clock. Nothing is broken. Time itself is passing more slowly for the moving system. This effect is called time dilation, and it applies to everything: clocks, biological processes, aging itself. Motion literally slows time. If you move faster, your time slows relative to someone at rest. This doesn't mean you feel slow. To you, everything feels normal, but compared to someone moving slower, your clock falls behind. No absolute winner. Here's the strange part. From your perspective, they are the ones moving, so you measure their time as slower. Both views are correct. Time dilation is not about who is really moving, it's about relative motion. Why this was so hard to accept. Before Einstein, time was treated as universal. Newton believed time flowed the same for everyone, everywhere. Einstein showed that was wrong. There is no single universal clock. There is no shared cosmic now. Each observer carries their own time. Time and space become one thing. Einstein didn't just change time, he unified time and space. They became part of a single structure called space-time. Movement through space affects movement through time. The faster you move through space, the slower you move through time. This trade-off is unavoidable. The speed limit of the universe. The speed of light isn't just how fast light travels, it's the maximum speed anything can move through space-time. You are always moving through space-time at the speed of light. If more of that motion goes into space, less is available for time. That's why time slows. This wasn't just theory. At first, Einstein's ideas sounded absurd, but they made predictions, clear, testable predictions, and physics lives or dies by experiments. In the next part, we'll look at how scientists proved time dilation is real, not once, not twice, but in experiments so precise that modern technology depends on them every single day. How we know time really slows down. The proof. Up to this point, time slowing down might sound elegant, logical, mathematical. But physics doesn't stop at ideas. It demands proof. And remarkably, time dilation is one of the most tested ideas in all of science. The first question scientists asked: if motion really slows time, then two clocks moving at different speeds should disagree, not by opinion, by measurement. So scientists did the obvious thing. They built clocks so precise that even a billionth of a second mattered. Atomic clocks, time made visible. Atomic clocks don't use gears or springs, they use atoms. Specifically, they measure how atoms vibrate at incredibly stable frequencies. These vibrations are so regular that atomic clocks lose less than 1 second over millions of years. If time slows even slightly, atomic clocks will notice. The first direct test: airplanes. In 1971, scientists performed a bold experiment. They placed atomic clocks on airplanes. Some flew east, moving faster relative to Earth's rotation. Some flew west, moving slower. Other identical clocks remained on the ground. When the planes returned, the clocks were compared. The result was shocking. The clocks disagreed. The airborne clocks had experienced time differently, not by accident, not by error, exactly by the amount Einstein's equations predicted. Flying faster made time slow down. Flying slower made time speed up relative to the others. Time had bent. This was not a one-time fluke. That experiment has been repeated many times since, with better clocks, better measurements, more precision. Every single time, the result is the same. Time slows in motion. Astronauts age more slowly. This isn't just laboratory science, it affects real people. Astronauts aboard the International Space Station orbit Earth at about 28,000 kilometers per hour. That speed is enough to slow their time. After months in orbit, astronauts return to Earth having aged slightly less than people who stayed behind. The difference is tiny, milliseconds, but it is real and it is measurable. GPS, the ultimate proof you use every day. Here's the most convincing evidence of all. If time dilation were not real, GPS would not work. Every GPS satellite carries multiple atomic clocks. These satellites move fast, about 14,000 kilometers per hour. According to Relativity, their clocks should run slower than clocks on Earth, and they do. But there's more. Gravity also changes time. This is where things get even stranger. Satellites are far from Earth's gravity, and gravity also changes time. Weaker gravity makes time run faster, so GPS satellites experience two effects. Motion slows their clocks, weaker gravity speeds them up. The net result? Their clocks tick about 38 microseconds per day faster than clocks on Earth. That might sound tiny, but for GPS, it's catastrophic. What happens if we ignore it? If engineers did not correct for this time difference, GPS errors would grow by several kilometers per day. Navigation would be useless, maps would drift, phones would lie. Every turn-by-turn direction you've ever followed relies on Einstein being right. Time dilation is not optional. It is engineered into the system. Time slows. Life doesn't notice. Here's something important. Astronauts don't feel time slow. Pilots don't notice it. You don't sense it on a plane because your body, your brain, your heartbeat all slow together. From inside the system, everything feels normal. Time only reveals itself when you compare two different motions. Why this isn't science fiction? Science fiction often exaggerates time dilation. Movies show people aging decades apart. In reality, that only happens near the speed of light. At everyday speeds, the effect is tiny. But tiny doesn't mean unreal. Gravity waves were once tiny too, until we built instruments precise enough to see them. Time is flexible, but not free. You cannot slow time at will. You must pay a price. That price is energy. As you approach the speed of light, the energy required increases rapidly. At light speed, it becomes infinite. That's why nothing with mass can ever reach the speed of light. Time slows, but it never stops. What this means for reality. Time is not universal. It is local, personal, dependent on motion. Every object in the universe carries its own clock, and those clocks do not always agree. In the next part, we'll explore what happens at extreme speeds, what time looks like near the speed of light, why astronauts could return younger, and why the universe enforces a strict limit on how fast time can bend.
When speed becomes extreme, how time almost stops. So far, we've talked about time slowing down at speeds humans can actually reach. Airplanes, satellites, astronauts. The effects were real, but small. Now we move into a very different regime. Speeds so extreme that time no longer slows gently. It nearly stops. Approaching the cosmic speed limit. The universe enforces a strict rule. Nothing with mass can reach the speed of light, not because technology isn't good enough, but because physics forbids it. As an object accelerates, its time slows,
but the closer it gets to light speed, the stronger the effect becomes. This slowdown is not linear. It accelerates rapidly. A thought experiment. 90% of light speed. Imagine a spacecraft traveling at 90% the speed of light. From Earth's perspective, time on the ship slows dramatically. For every 10 years that pass on Earth, only about 4 years pass on the spacecraft. Already, time is behaving in a way that feels almost unreal. But we're not done yet. At 99.9% of light speed. Now increase the speed to 99.99% of light speed. For every 10 years on Earth, the astronauts experience just over 1 year. Civilizations could rise and fall on Earth while the crew ages only slightly. And still, this is not the extreme case. At 99.999% of light speed. Push even closer. At 99.9999% of light speed, the difference becomes astonishing. Thousands of years could pass on Earth, while only months pass for the traveler. From the traveler's perspective, the journey feels short, aging slows dramatically, and time feels normal. But from Earth's perspective, the traveler is almost frozen in time. This is where intuition breaks. It feels like cheating, like time travel. But it isn't. No one goes backward in time. No laws are broken. Time simply flows at different rates for different observers. Relativity allows this because there is no universal clock. The energy wall. Here's the catch. As you approach light speed, the energy required to keep accelerating increases without limit. At 99%, you need enormous energy. At 99.9%, far more. At 99.999%, the energy requirements become astronomical. To reach light speed itself would require infinite energy. That is why nothing with mass can ever reach it. The universe protects its speed limit by making it unreachable. Why time never fully stops? From Earth's perspective, the traveler's time slows towards zero, but it never reaches zero. Time does not stop. It only approaches stillness. This ensures causality remains intact. Events still happen in order. The universe stays consistent. Sci-fi versus reality. Science fiction often shows characters moving at light speed with time completely frozen. That makes good drama, but it's wrong. In reality, time never fully stops. Light speed is never reached. Infinite energy blocks the path. Relativity is strange, but it is precise. The twin scenario without paradoxes. You may have heard of the twin paradox. One twin travels near light speed, the other stays on Earth. When the traveler returns, they are younger. This isn't a paradox at all. The traveling twin changed frames of motion by accelerating and turning around. The earthbound twin did not. Different paths through space-time result in different amounts of time experienced. No contradiction, just geometry. Time as a path, not a flow. This leads to a powerful idea. Time is not something that flows, it is something you move through. Your motion through space-time depends on your velocity. The faster you move through space, the slower you move through time. This trade-off governs the universe. Why this matters beyond science fiction. Extreme time dilation isn't just a curiosity. It explains why the universe has a speed limit, why causality holds, why physics remains consistent. It also shows how deeply motion shapes reality. Time is not separate from movement. They are two sides of the same structure. The final question. If motion can slow time this dramatically, why don't we notice it in daily life? Why does time still feel so steady and absolute? That question brings us to the final part of this journey. In the next and last section, we'll pull everything together. We'll explain why time feels constant, even though it never truly is. Time was never what we thought. Time feels steady. It feels like the one thing in the universe we can trust. Seconds pass, minutes follow, life moves forward. And for most of human history, that was enough. But the universe tells a different story, a quieter one, a stranger one. Time does not flow the same for everyone. It bends, it stretches, it responds to motion just as space does. If you move fast enough, time slows down. Not because you feel it, not because you choose it, but because the universe requires it. This isn't science fiction. Your phone depends on it. Satellites correct for it. Astronauts experience it every day. Time is not a background stage where events play out. It is part of the structure itself, linked to space, shaped by motion. There is no single now shared by the universe. Each observer carries their own time, their own clock, their own slice of reality. That idea feels unsettling because it challenges something deep, the belief that time is absolute. But it also reveals something remarkable. The universe is not rigid. It is flexible, consistent, and more elegant than we ever imagined. We are not drifting through time. We are moving through space-time. Every step forward is a balance between motion and duration. And no matter how fast we go, no matter how close we approach the limits, time never breaks. It adjusts. The next time you look at a clock, remember this. It isn't just measuring seconds. It's recording your path through the universe.